Hi, my name is Gareth. Welcome to this introductory talk about Simultaneous Localization and Mapping, or SLAM as it is often abbreviated. This talk is intended as a high-level introduction. We're going to give an overview of what SLAM is, investigate a conventional visual SLAM pipeline as used with computer vision, and then look at some high-level design trade-offs that you might encounter in a SLAM problem. So what do we mean by SLAM? So SLAM refers to a two-step process whereby we must simultaneously localize and map. By localization, we mean recovering the state of a vehicle or a sensor platform, usually over multiple time steps. So for example, you might be interested in the position and velocity of your drone, or in the position and orientation of your AR headset or of a cellular device in the case of a mobile AR application. And in the process of doing so, you typically have to build a map that is recovering locations of some landmarks in a common reference frame. You need the map to compute your location, and you need your location in order to build the map. And so this process has to happen simultaneously. And that's what SLAM is doing at a high level, is iteratively recovering these two quantities. Now, you could argue that we've been doing this for a very long time. For example, early sailors could navigate the Mediterranean by adhering to coastal waters and recognizing specific recognizable visual landmarks as they sailed. So as you move, you can imagine identifying landmarks you know on the coastline, and then from that you can get a sense of how you're moving, and then as you move, add new landmarks to your mental map. Of course, this is prior to the innovation of astral navigation using the stars. So the process of accumulating that knowledge is the mapping step, and then the task of recognizing where you are using that knowledge is the localization step. I like this map here. It's an early map of the world developed by Eratosthenes. It reflects kind of an interesting property in SLAM and state estimation, which is that where more data is available, the accuracy is generally going to improve. So from this map, as you might imagine, most of his data was collected around the Mediterranean, and that's where the map is the highest quality. Elsewhere, of course, it looks a lot more approximate. So technology has improved a lot over time by orders of magnitude, in fact. So this visualization is a 3D reconstruction of Rome, built from tens of thousands of images using a process called structure from motion, and we're going to come back to what that is in a little bit. But for now, all you need to know is that these red triangles reflect the positions and view angles of camera images, presumably captured by tourists. And then the points are 3D points that we have triangulated with those cameras in order to build a high-level or a high-quality reconstruction. So this kind of technique, it can actually map the scale at we can map the world at a scale of centimeters or even better, and it can also scale from very small problems, like a few photographs on a cell phone, to massive problems at city scale, like this one here. And you can actually see the same property reflected in this map as in the previous one, which is that where the data is most dense, presumably by the Colosseum, since people will photograph it the most frequently, the map is very dense and very high quality, and then elsewhere it is not.